So if you got any questions based on what I have discussed so far, you may ask me now. Otherwise, I can proceed today's lecture. If you got any questions based on whatever we have discussed so far, I'm happy to answer. Okay, so it indicates that no questions. So we'll move on to the production processes. I'll start with fertilizers and some of the bulk chemicals. So we will see various production methods, how a process plant works of some of the fertilizers and chemicals. So fertilizers. What is a fertilizer? Fertilizer is a material that applied to soil or to plant tissues to supply one or more plant nutrients which are required for the growth of the plants. Basically, fertilizer is a material that's applied to supply, that is used to supply one or more nutrients for the growth of the plants. So, for the growth of the plant, certain nutrients are essential. We supply that in the form of fertilizer. There are 6 primary nutrients. First 3 are carbon, hydrogen, and oxygen. For the plants, carbon can be taken from CO2 in the air, photosynthesis. Hydrogen and oxygen are taken from the water. Oxygen can also be taken from the air by the plants. So these 3 are naturally, you don't need any additional thing. Water, air, that is there in the soil, in the atmosphere. So these 3 nutrients can be taken. Apart from these 3, another important nutrient is nitrogen. Nitrogen helps plants to make the proteins they need to produce new tissues. How the plant grows. The growth of new tissues only make the plant to become bigger and bigger and bigger. So the production of new tissues by the proteins helps by this nutrient nitrogen. Another important nutrient is phosphorus. Phosphorus stimulates the root growth. Phosphorus stimulates the roots growth. Also helps the plant to set buds and flowers. Plants to set buds and flowers. So organic matter in the whatever organic matter present in the soil or microbes present in the soil, that activity also will be increased with the help of phosphorus. The another important nutrient is potassium. It basically improves the overall vigor of the plant. It helps the plant to make carbohydrates and also provides disease resistance. Potassium help the plants to produce more resistant to diseases. So we all know NPK. NPK are the three important nutrients. Those often needs to be supplied additionally. NPK are the three nutrients. Those nutrients has to be supplied in the form of fertilizers. In the olden days, before the invention of the synthetic fertilizers, potassium nitrate, sodium nitrate reserves were available in many places. Potassium nitrate, sodium nitrate, they used to mine from the reserves and use as fertilizers. In the early 19th century, people have found that the reserves of potassium nitrate, sodium nitrates are decreasing, then explored various ways to produce these fertilizers, these various ways to produce synthetic fertilizers. So there are two types of fertilizers, organic and synthetic fertilizers. Organic fertilizers made from naturally occurring mineral deposits. Also organic materials such as bone or plant meal or composted manure. Sorry, hope my voice is clear. So organic fertilizers are made from naturally occurring minerals or organic materials such as bone or plant meal or composted manure. So composted manure, if at all you're from villages, you will get to see this one. But of course nowadays no one using this. But when I was a child, a lot of farmers used to use this. Although very less of bone or plant meals which I see, but composted manure was common. And I described a few minutes back the deposits of potassium nitrate, sodium nitrate, that the naturally occurring minerals also used as an organic fertilizer. Okay. Whereas synthetic fertilizer is made by chemically processing of raw materials. We artificially, by processing certain raw materials, we produce the fertilizers. Those are called synthetic fertilizers. Organic fertilizers are not water soluble. Organic fertilizers are not water soluble. Hence, they are released to plants very slowly. Hence, they are released to the plants very slowly. Because the fertilizers are applied to your soil, and the fertilizers which are not completely water soluble doesn't mean that it is very mildly soluble. Solubility is very low. The organic fertilizer solubility is very low. Not completely water soluble, but mildly soluble. Maybe I should put as mildly water soluble. Okay, I should change it. Mildly water soluble. Since the solubility is very low, the release of the nutrients to the plants is also slow process. Whereas synthetic fertilizers like urea or DAP, these are water soluble. Since all the fertilizer is water soluble, the plants can take immediately and you can see the growth immediately. So now what is the merits and demerits of these fertilizers, organic and synthetic fertilizers? Organic fertilizers stimulates the soil microorganisms, stimulates the beneficial soil microorganisms. Like one of the important beneficial soil microorganisms is earthworm. So when you add these organic fertilizers, earthworms, the growth of the earthworms will be stimulated very well. And because of this growth of the soil microorganisms, it improves the structure of soil. It not only gives the it not only gives the nutrients to the plants, it also maintains the soil quality. But in opposite, when you use synthetic fertilizer, since they're readily soluble in water, what happens is the plants take some nutrients and whatever it doesn't take, that leaches into streams. Like if you have a many fields, right, water flows from one point to another point continuously. So whatever this soluble in water, that is floats on the top. If if plants take the nutrients, well and good. If doesn't take, they go along with the leaching water. It will go along with the water. Also, this synthetic fertilizers doesn't enhance the soil texture. It doesn't improve the soil properties. It doesn't improve the soil property. It gives nutrients to the plants, but doesn't enhances the soil quality. So now whether we need out of these three nutrients NPK, as we discussed NPK, what type of a synthetic fertilizer is needed for a specific area, specific field, is depends upon the soil test. So before they use fertilizer, they should perform soil test. What mineral is less available in that soil, whether it is nitrogen or whether it is phosphorus or whether it is potassium. Based on the need of the soil, they should select whether nitrogen-based fertilizer or phosphorus-based fertilizer or potassium-based fertilizer or mixture of three. So unfortunately, people doesn't perform the soil tests. They randomly put these fertilizers, and that also causes the big problem to the soil. So soil test is performed to see what is the available nitrogen, available potassium, available phosphorus content, and whatever is deficient according to the regulations, they should add the required fertilizer quantity. Hope you all understand it. Students, do you have any questions so far? Probably you're aware of most of these things, but I thought in a way, in a way to start to give a overall picture, I'm just explaining some of the basic details. Right. Why I have started this is agriculture. I showed also in the first class. Agriculture contributes almost 17.1% of the country's gross value. The agriculture contributes almost 17.1% of the country's global value. And according to Census 2011, 54.6% of the population is engaged in agriculture and allied activities. Unfortunately, it is reducing, but it used to be the major percent of the population engaged in these activities. Now, food grains production is also increasing year by year. In our country, food grains production is also increasing year by year. When we got independence, close to that, we used to produce 52 million tons of food grains annually. Recently, in 2018, 2019, I didn't get the recent data. Only this is available in Department of Fertilizers, Government of India website in 2018, 2019. In 2018-2019, 284.95 million tons of food grains are produced across the country. So it's huge quantity. Now to get this much crop production or food grains production, you can imagine how much amount of fertilizer is required across the country. So the need for fertilizer is very, very high. The government of India has started just post-COVID or in the mid of 2021. Some of the very old fertilizer plants, government of India closed some of the industries almost 15 years back. But again, they started functioning back because the need for production of fertilizer is increasing. So, what are the fertilizers produced in India? At least to give you a quick idea. So, we have public sector companies and we have corporate and we have private sector companies are there. Uh, like various fertilizer industries are there. Public sector fertilizer industries, corporate sector and private sector. All the three are there. So we produce three types of fertilizers in India. One is urea, another one is DAP, diammonium phosphate, another one is complex fertilizers. Complex fertilizers is contains both, all three, N, P and K. In case of urea, this only contains nitrogen. In case of DAP, diammonium phosphate, it contains nitrogen and phosphorus. In case of complex fertilizer, they add potassium also. We don't have potassium reserves in our country, and those potassium has to be imported from foreign countries. So that production is little less compared to others because we need to import most of the potassium raw materials from foreign countries. So, and you can see the total amount of fertilizers produced of three, urea is very high, almost 240 lakh metric tons. Lakh metric tons are produced in India. DAP is almost 40 and complex fertilizer is almost 90 lakh metric tons. So you can see the amount of, it's a huge quantity, 200, almost like on an average, 350 lakh metric tons are being produced. Now, what are we importing? 25% of the requirement of urea raw materials are imported, and 90% of the phosphates and 100% of the potassium are being imported. Phosphates and potassium reserves are very, very low, or it was there, they used to be there, we have reserves, but are completely used during the Second World War. Whatever potassium and phosphates are completely used by the so-called rulers at that time during the World War. So all our reserves are gone. So now we are importing. So because of this importing these phosphates and potassium and some of the urea raw materials, the cost is very, very high. The cost of production will be very, very high, which a common farmer cannot afford. Hence, the government of India gives subsidy every year. Now, the subsidy paid by the government of India is almost 70,000 crores. Almost 70,000 crores to get that price which is available for the farmers. So, how urea is being produced, or what is important raw material in this to produce synthetically, to produce these fertilizers synthetically, urea or DAP, a complex fertilizer. What is the important raw material to produce these three fertilizers is ammonia. Ammonia is the important raw material or important reactant in producing the DAP or urea fertilizer. Like you can see here, when ammonia reacts with CO2, ammonia when reacts with CO2, it produces urea. It produces urea. When ammonia reacts with CO2, it produces urea. When ammonia reacts with nitric acid, that produces ammonium nitrate. Ammonium nitrate. Now again, how do you produce this nitric acid? If you oxidize ammonia, you will get nitric acid. If you oxidize ammonia, you will get nitric acid. Similarly, if you react phosphoric acid with ammonia, you will get ammonium phosphate. Ammonium phosphate. So here we get various types of phosphates, mono, di, and triammonium phosphates. So DAP is diammonium phosphate. Similarly, if you react with sulfuric acid, you will get ammonium sulfate. So ammonium phosphates, ammonium nitrates, urea, ammonium sulfates, they are all produced from the ammonia, and these are all used as a fertilizers. These are all used as a fertilizers. So in the fertilizer production, important raw material is ammonia. So in the early 19th century, uh, need for ammonia became tremendously very increased because the fertilizer production is should be needed very high, and hence ammonia, urea fertilizers is required for urea, ammonia is required, and also nitrates, ammonium nitrates is also used as explosive material during World War and at the early 19th century. So the need for this one is very high. Demand for this is very high. So with ammonia we can produce many other components and important components, acrylonitrile, MEA, other components. So first we will see, since ammonia is the base material to produce this fertilizer, first we will talk about ammonia. Also, ammonia is important bulk chemical. So first we'll start with ammonia production. Ammonia production is the first large-scale synthesis at high pressure and high temperature. Earlier I have showed you sulfuric acid is the first large-scale plant, but that is at normal temperature. Whereas ammonia or atmospheric pressure, sulfuric acid is atmospheric pressure. Whereas ammonia production is the first large-scale synthesis chemical industry which is carried out at high pressure and high temperature. The pressure is more than 100 bar and the temperature is around 700 Kelvin. So we all know it, this famous Haber-Bosch process. Nitrogen reacts with hydrogen and produces ammonia. So it is a reversible reaction. It is a reversible reaction. And for this reaction to happen, catalyst is must. Without catalyst, if you try to produce, if you try to carry out this reaction, the conversion is almost 1% only. The conversion is lower than 1%. Without catalyst, if you try to carry out this reaction, even at very high pressure, this N2 plus 3H2 gives 2NH3, the conversion value will be much lower than 1%. That means it's almost impossible. And this is an exothermic reaction. And this is an exothermic reaction. And you can see heat produced is very high. The heat of reaction is very high. Minus 91.44 kilojoules per mole. One mole almost produces 92 kilojoules of heat. So highly exothermic reaction, and it requires catalyst. Without catalyst, if you try to carry out this reaction at whatever temperature, whatever pressure conditions it may be, you will get conversion close to 1% or lower than 1%. Hence, the need for catalytic reactions at high pressure, high temperature is there. And Haber has first invented this method, and I'm sure you all know that he got Nobel Prize for inventing this. And for commercially developing this process, Bosch got the Nobel Prize. And you know, these two chemical engineers, they invented the process, they have started industry, and they have produced it, and they own it till now. The patents are till now, the royalties are being, till now is going to their children's or grandchildren's. Many people say startup, startup, but almost 1908, the Haber and Bosch, they invented a chemical reaction, they constructed a chemical process, they erected an industry, they commercially produced ammonia, and they supplied it, and they own patent. The royalties are being going to their family members even after 100 years. So that is the thing. Even many IIT graduates want to become entrepreneurs. They only seeing only one direction, software. But if you invent your own process, if you invent your own chemical engineering method, which you all have the ability to do, you can make your own startup. Like when I did my PhD, I have developed a method, and I have produced very cost effective way to produce nanomaterial. Now there is a high chance that I can do startup, but considering my tendencies, my own interests of teaching and research, I didn't go into that direction, but there's a very good chance. So, if you want to become an entrepreneur, I think you should read this Haber and Bosch story, and I think get some inspiration to go deep into chemical engineering because it has a lot of potential. Trust me, it has a lot of potential. Right. So you can see in 1913, first plant produced by the BASF chemical industry by Haber and Bosch. They started with 30 tons per day. They started this process 13 tons per day. Now you can see in 2000s is almost after 90 years. It is 1750 tons per day. And I'm sure you all know royalties means, right? Every single penny, every single rupee produced or earned by this certain ratio goes to that inventors. So you can imagine 1750 tons per day in year, how much tons goes and how much cost of the production of ammonia comes and how much royalties are going to this family members of this Haber and Bosch. So that is the beauty. Once you invent something, it stays with you for a long time. That's why innovation is very important. Innovation is the key. And to get some innovation, we need to do some research. We need to spend some time and effort. So Let's whenever we take a reaction, whenever we take a reaction, before we go to a process plant or industry, how it operates, we need to look into two things. We need to immediately look into two things. What is the thermodynamics of that reaction and what is the kinetics of that reaction? Whenever we see a reaction, before we go into the details of an industry or process plant or flow diagram, we need to know three aspects. We need to know three aspects. One is what are the thermodynamics of the reaction. Then we need to know the kinetics of the reaction. And one is whether it is complete conversion or partial conversion. Whether complete conversion happens or partial conversion. We need to look into these three aspects. Why do we need to look into thermodynamics? Any guess from any students? What thermodynamics gives us? I think you already learned chemical engineering thermodynamics. Any idea what the thermodynamics tells us?
Temperature decision based on endothermic or exothermic.
Temperature based like okay, endothermic and exothermic.
Sir, feasibility of the reaction.
Very good. Feasibility of the reaction is known from the thermodynamics, whether this is possible or not. Very good. Any other? One more also we can find out. Endothermic, exothermic, feasibility, and one more thing. In chemical reaction equilibria, you might have solved some problems in thermodynamics. Equilibrium conversion value. Have you remembered? Equilibrium conversion. In chemical reaction equilibria chapter, you must be solved some problems on equilibrium conversion. Have you done? At least I remembered those problems. You may not know the only process, but okay. So the third thing we can learn from thermodynamics is equilibrium conversion. Equilibrium conversion means what? Maximum possible conversion at the temperature and at the pressure conditions. From thermodynamics, we can tell whether it is exothermic, endothermic, that is from the reaction data. Second thing is whether its reaction is possible or not, we can tell. And third thing is we can also estimate equilibrium conversion. Equilibrium conversion means maximum possible conversion at the temperature and at that pressure. From the thermodynamics, if the maximum possible conversion is 1%, we don't need to do any reaction. We don't need to do any we don't need to carry out a practical reaction. So in CAPE course, while I teaching, I will show you using Aspen how can we calculate this equilibrium conversion value if you missed in thermodynamics. So that is thermodynamics. From kinetic data, what we get to know? From kinetics of the reaction, what we'll come to know? What information we'll get to know? Any guess from the students? Even if wrong, no problem. If you feel something, please tell.
Speed of the reaction.
Yeah. How fast the reaction happens at the temperature and at that pressure? Rate of reaction, right? Kinetics means rate of reaction. How fast the reaction happens at that pressure, at that temperature? Is it a matter? How fast reaction happens, is it a matter or not? Is it important or not? How fast reaction happens, is it an important thing or not? If yes, why? If no, why? Any guess from the students? See, I don't even
Yes.
know. Yeah, why it is important? Answer is yes. Why is important?
We need to produce a certain quantity of it in a day. So
Okay, yeah, we need to produce certain quantity in day. If it is slow, suppose let's say it is slow, what will happen? We need large process vessels, right? Huge and huge. Maybe I'll explain in a simple way where you all can understand. Have you heard about residence time in reaction engineering?
Yes, sir.
Yeah, residence time. Very good, you heard about it. If high residence time means what? When the reaction is fast or slow? Any relation between residence time to the speed of the reaction, rate of the reaction? So for fast reactions, we need low residence times. For slow reactions, we need high residence time. Residence time means the time in which the reactant spends in the reactor. Let's say this is PFR. Let's say this is a plug flow reactor. So if it is slow reaction, that means more time the reactant has to stay in the PFR. Am I right? Let's say the reaction is slow reaction. The reactant need to spend more time in the plug flow reactor. Am I right? Is that correct or not? Let's say I'm a slow eater. Do I need to spend more time before the plate or not? If I'm a fast eater, I don't need to spend more time near the plate. Similar logic. If slow residence time or if reactance is slow, the speed of reaction is low, that means it needs to spend more time in the reactor because for the reaction to happen. That means high residence time. High residence time. Slow reaction, high residence time. Fast reaction, low residence time. Any student saying something? So, what is residence time? We all know it. Volume of the reactor by volumetric flow rate of the reactant. Have you heard about this? V by Q.
yes,
Yeah. So, so this is equal to residence time. Let's say T. The volumetric flow rate is constant. The reactant inflow will be always constant. If high residence time means high volume. High residence time means high volume. Residence time is volume of the reactor by volumetric flow rate. Input is always constant. Input to the reactor is always constant. So, or we may say for a given input, if you have high residence time, we need higher volume of the reactor. High residence time when happen? Slow reactions. For slow reactions requires high residence time. High residence time means higher volume of the process and the higher volume of the reactor. So when the reactor volume is big, everything becomes big. The construction, of the reactor will become expensive, maintenance will become expensive, utilities for the circulation of water and all will become difficult. So the kinetics is also important. How fast reaction happens information is also important because that tells us what residence time we need to maintain, that tells us what is the volume of reactants required, that tells us everything else. Do you all understood why the kinetics is important? Got some idea why you have learned at least CRE or why you have learned thermodynamics? Probably you understood. So conversion at the temperature and pressure, whether it's 100% conversion or less than 100% conversion, we need to know. Let's say if conversion is less than 100%, let's say 30% conversion. Why is this important? Why we need to know whether it's partial conversion, full conversion? Why do we need to know? Let's say this is reactor and A gives to B is happening. A gives to B is happening. Let's say we are sending A here and we are getting products. We are getting products after the reaction. Now, if the conversion is let's say less than 100%, let's say conversion is 30%. What all will come as a products? What are the things will come as a products? If conversion is 30%, what are the things will come as a products? Any guess? Maybe I'm asking. Yeah, maybe I'm asking very silly questions. So A and B we get. If it is 100% conversion, you will get only B. If it is 100% conversion, we get only B. So we don't need any additional unit operations to be carried out after that because we get a pure B. But if it is in reality, we'll never get 100% conversion. That we do. So less than if it's 30% conversion, we have A and B. So what we need to do immediately after the reaction, if you want to enhance the what is this profit or loss of A, when you get more profit, when you utilize A more, right? When you will get the profit of the process very high, when you utilize more A, am I right? A is the reactant and B is the product. And if A is less converted, if A is not fully converted, what will happen? We are wasting A, right? Am I right? So if the conversion is less than 100%, what we need to do immediately after the reaction, the reactant needs to be separated. The reactant needs to be separated. That means there must be a separator and reactant needs to be recycled. This, to get this information, we need to know the conversion. Why we need the information of conversion? If conversion is low, we have to immediately devise a unit operation after the reactor that should separate reactants from the products. That reactant has to be recycled. Then only we will be able to utilize the more amount of A. Then only we can utilize the full amount of A. Otherwise, the profitability of the process will be very, very low. I have given very basic but very, very good information in a simple words. Hope you all understand it. Do you understood why thermodynamic, kinetic and conversion is important? If you got any questions, please ask me because these are very simple and important details and very crucial. If at least one student says I understood, I can proceed next.
Yes, sir.
Okay. If anyone did not understood, please discuss among your friends or you can always ask me. I know this is simple, but simple to understand, but if you don't understand by any chance, you can always ask me. So, let us see the thermodynamics of this ammonia reaction. N2 plus 3H2 gives ammonia. So, thermodynamics, every thermodynamic data graph will have either conversion or ammonia content in the y-axis. So, this is the reaction N2 plus 3H2 gives to 2NH3. So whether it's conversion of nitrogen or ammonia content, both are interrelated. So y-axis sometimes they will say conversion or sometimes they will put in terms of product content. So mole percent, if 100% ammonia is present in the product means completely reacted. If less percent of ammonia is present means less reacted, partial reacted. So x-axis will be temperature and we have different lines and different pressure. So this is a 1000 bar pressure, this is a 400 bar pressure, this is 300 bar pressure, 200 bar pressure. So this I have taken from the Mawalji book. I have already listed in the textbooks in the first class. Please refer to that book. I request all of you to download from the web. So that will be useful for your reading. So now we can see here as the temperature increases, as the temperature increases from almost 550 degrees centigrade, almost 550 degrees centigrade, the ammonia content that is decreasing. Ammonia content directly correlates with the conversion. The conversion is decreasing. As the temperature increasing, the conversion is decreasing. The same thing is observed at all pressures. At all pressures. But one important thing we are observing, as the pressure increasing, as the pressure increasing, ammonia content is increasing. That means the conversion is increasing. The conversion value is almost 92%. The conversion value 92 to 93% at 1000 bar pressure. So why with increasing pressure, why this ammonia is increasing, content is increasing, or conversion is increasing? Why with increasing temperature this is decreasing? Any guess from the students why this has happened? Any guess? Very simple. Very simple. We have forward reaction and we have the backward reaction. Always remember, whenever we have reversible reactions, whenever we have reversible reaction, high temperature favors backward reaction. Whenever we have a reversible reaction, high temperatures favors backward reaction. High temperatures favors backward reaction. So instead of nitrogen to hydrogen, the conversion from ammonia back to the nitrogen to hydrogen will be more dominating. More dominating. So that's why when the temperatures are increasing from 550 to higher temperature, you will get more backward conversion favorable. Hence, the ammonia content is decreasing because more and more ammonia is dissociating back to the nitrogen and hydrogen. More and more ammonia is dissociating back to the nitrogen and hydrogen. Now, when increase the pressure, when increase the pressure always favors the forward reaction. Increase of pressure favors the forward reaction. Hence, at high pressure, this too is applicable for reversible reactions. Reversible reactions. So that's the reason high pressures giving more amount of ammonia and at high temperatures less amount of ammonia. See here, this condition is giving almost 92% conversion. It's very, very good. But I have shown in this figure that in this gray area only industrial plants operates. Only in this gray area industrial plants operates. What could be the reason? Any guess from the students?
It's a law of thermodynamics.
What is that? Can you explain a little bit?
I mean that I guess the maximum efficiency something.
This is from the thermodynamics alone. So maximum conversion we are getting at 92%, but they prefer to operate at lower conversion, like 35%. Ideally, we wanted high conversion only, but for the economics point of view, they're operating at low. I'm giving clue. Any guess now? Is it good, easy to operate very high pressure? Uh, let's say if you operate at 100 bar pressure, we need very thick vessel, very thick reactor, right? In the equipment design, I think you have you started equipment design course? Not right. Student equipment design course already over. Just to know only.
Yes, sir. Over.
Yeah. So thickness of a pressure vessel is depends upon the pressure. If you want to maintain high pressure, we need to maintain highly thick pressure vessel, and also very difficult to control this torus head. So maintaining very high pressure will become very expensive. It is very difficult both for the safety reasons and also for the fabrication of the reactor works. That's why we operate low pressure. And why at high temperatures they prefer than the low temperature? That we will know from the kinetics. So I think it's already 10 o'clock. So 10:59. So we'll stop here and we'll continue in the next class. So we'll continue why we are operating at high temperature and low temperature, that I'll explain in this class. That comes from the kinetics information. Is that the reaction rates are high at high temperature, reaction rates are low at the low temperature. So with more details, I will explain in the next class. Okay, thank you so much. If you got any questions, kindly ask me, otherwise we'll stop here.